A standard 110-volt industrial outlet is everywhere on a job site. It powers our tools, our lights, our equipment. But this everyday power source hides a dangerous dual nature. In one scenario, a worker brushes an exposed wire and feels only a harmless static pinch. Yet another worker touches that exact same wire, and their muscles lock up in a violent, uncontrollable spasm as they collapse. If the equipment and the power source are identical, how can the physical outcomes be so drastically different? The answer lies in how we measure danger. We label equipment by its voltage, but in occupational safety, voltage is merely potential energy. Survivability is dictated entirely by a different metric, the actual electrical current driven into the body. When training new workers, you often see a heavy reliance on warning labels. They look for the high voltage signs, assuming those dictate the boundaries of workplace safety. Treating voltage as the sole indicator of danger creates a massive blind spot. It ignores the specific physical conditions present at the moment of contact, a mistake that regularly leads to preventable fatalities. To understand the real threat, you have to look at the worker not as a victim, but as a variable electrical component inserted into an active circuit. The true mechanism of physical injury is the current. Current is the actual volume of electrons flowing through the tissue at any given second. Preventing electrocution means calculating exactly how the human body resists or conducts that incoming current. The mathematical bedrock for understanding electrical lethality is Ohm's law. Current, represented by I, equals voltage divided by resistance. Let's plug in the numbers for a standard exposure. We will set the voltage at a constant 110. The resistance will serve as our variable. Under ideal conditions, human skin is a highly effective electrical insulator, provided it is perfectly dry. Occupational safety data shows that completely dry skin provides an electrical resistance of 100,000 ohms. If we divide our 110 volts by 100,000 ohms, the resulting current is 0.0011 amps, or roughly 1.1 milliamps. At just over 1 milliamp, this current is a tiny fraction of what causes physical harm. The body's natural dry resistance successfully repelled the electrical pressure. This calculation perfectly explains the harmless static pinch from our first scenario. But industrial environments are rarely perfectly dry. Physical exertion generates sweat, altering the physical properties of the skin. The salt and moisture from minor perspiration alone can reduce human skin resistance by a factor of 200. In an instant, the protective barrier of 100,000 ohms plummets down to a mere 500 ohms. Run the Ohm's law calculation again, dividing the same 110 volts by the compromised 500 ohm resistance. The output spikes to 220 milliamps. The equipment's voltage didn't fluctuate at all, yet by simply sweating, the internal current driven into the tissue multiplied by 200. Environmental moisture acts as a hidden catalyst, instantly converting a standard, seemingly manageable voltage source into a high current hazard. This chart maps how electric currents impact our nervous system. Our dry skin calculation of 1.1 milliamps lands safely on the far left, but our wet skin calculation of 220 milliamps sweeps aggressively to the right, directly into the heart fibrillation zone. An external electric shock sends currents through the tissue that are many times greater than the tiny natural currents communicating within our own nervous systems. This massive electrical override induces fibrillation. The electrical noise causes the muscles to freeze or cramp into violent, involuntary contractions. At 220 milliamps, this contraction is severe enough to instantly paralyze the respiratory system or stop the heart entirely. If the victim is holding the conductor, the involuntary muscle freeze prevents them from letting go, locking them into the circuit until power is cut. Because the fatal current threshold is easily crossed with simple physical exertion, relying on the body's natural electrical resistance is a failed, deadly safety strategy. To manage this risk, we must look away from the internal mechanics of the body and focus on how current navigates the external workspace. Current seeks conductive pathways. This often starts with direct exposure points, like degraded insulation on common cables, that leaves the interior wiring bare. Even more dangerous are the secondary conductive paths that workers forget to account for. Heavy metal equipment, like an ungrounded aluminum stepladder, can easily become a massive conduit. Alternate power setups, including common DC sources like heavy-duty batteries or photovoltaic cells, present the exact same biophysical risks of establishing a current path. Preventing a fatality relies on isolating every single potential point of physical contact before the worker's body ever has the chance to enter the circuit. Safety professionals categorize these catastrophic end states using a comprehensive hazard model known as the Be Safe framework. The S and E represent shock and electrocution, the direct internal biophysical traumas we've mapped out. The B and A stand for burns and arc flashes. These occur when high-voltage gaps break down the air, releasing violent thermal energy. Finally, the F and E cover fires and explosions, the large-scale environmental catastrophes triggered by that runaway energy. Every single one of these 6 outcomes stems from the exact same root cause, a failure to properly control the physical relationship between voltage, resistance, and current. Relying on warning labels is reactive. True prevention is achieved through active environmental engineering, mitigating dampness, removing ungrounded conductors, and rigorously insulating every potential path. Understanding the strict physics of electrocution is the difference between blindly hoping a worker avoids contact and actively designing a workspace where contact is impossible.